Alright, time for another DraftPhysics.com video presentation. So the Ian Gostling has made a video, and it's not horribly rude, so we'll play it. And I just don't understand. I just don't understand how this is an argument in defense of whatever it is they're defending, because it basically proves what they're defending doesn't make much sense. So
everybody.
So he said, "Hello, everybody." I don't think everybody's here, but yeah, that's just part of the internet. It's a lot shorter of everybody. Okay.
Gary, I know you was a bit worried. I think you're missing me. I'm all right, thank you, mate.
No, I wasn't missing you. So, especially wasn't missing your older videos where you claim proofs and the proofs are not proofs. I mean, all of that just adds noise to the whole conversation. It isn't very helpful. So I wish you wouldn't do that. Blah, 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 blah.
Yeah, I suppose I lost a bit of interest in making the videos because you weren't dealing with them, so...
Well, you're not dealing with my arguments, so you can sort of see that, I think I'm making the accusation first. I mean, yes, I did make the entire arguments 5 minutes long, okay? Not just an experiment, but just the whole theory. 5-minute long videos about the theory, all right? And none of you can responsibly point out how what I'm arguing has been proven wrong.
Well, I lost motivation there. But this one...
The volume is just weird on this video, sorry. It's hard to get it exactly right.
It's really about defending physicist Michael.
Which I don't really understand, because the first lie, okay, of his lever video was not acknowledging that the equal mass experiment came out completely differently than he predicted. So, just for your information, apparently. I mean, apparently you're not aware of the fact that his prediction was completely different than the outcome, indicating his model failed, okay? And he didn't take any responsibility for that. I mean, none. He didn't say a thing about it. So obviously I predict that the energy goes in, and all we're looking for is this arrow to come out somewhere. So as a mass and a velocity, we're just saying we put this much in. We're saying somewhere in this experiment, right? We just call this a box. We're just putting an MV into the box. All right, and you just say, well, yeah. We're just saying, okay, we want to see that pop out somewhere. It could pop out over here. It could pop out over here. It could pop out in pieces, a little piece over here, a little piece over here. But we have to have a total of it pop back out of the box. That's my simple theory. Now, his theory is that the energy goes in one direction, and what we have to look for is a total, okay, of, we have all kinds of directions, but the total direction has to pop back out of the box. So he's saying he doesn't care about the magnitude of the arrow, the amount coming out. He just cares about this here direction. So he's saying after everything happens, this has to come back out again in the same direction. And it doesn't matter if there's pieces this way and there's pieces this way and there's pieces all kinds of ways. They just can't be ways this way without totaling. And so by his explanation, he's saying that two amounts of momentum, one went in here, two of them went into the fulcrum-y thing, and half and half came out here, so a total of one came out going the other way. So out of the box came one arrow going this way, a total of one. So these two cancel, and this is what you're left with. And so that matches this. That was his theory. Now, his theory didn't turn out, okay? This didn't happen. This 1/2 thing didn't happen. I'd say this 2 thing never happens. The fulcrum didn't move. The whole point is for this not to move, for this not to have momentum. All right, and this half here didn't happen either. Okay, this was a hole. Okay, almost. So 90%-ish. 90% by velocity anyway. And we can assume, okay, not a terribly crazy assumption, that the other 10% of the energy was in the swing of the lever. Now, obviously another lie of his is that anybody cared about whatever angular momentum was. That was somehow part of this experiment, that anyone was concerned with some sort of angular momentum. When we know the carts were on tracks, okay? The carts couldn't possibly have angular momentum because it was a dead straight track that the carts traveled on. And they can't angular, okay? And so clearly angular momentum wouldn't be something of interest. And even more clearly, measuring the angular momentum of the lever itself after the experiment's over and the lever's still moving, well, double who cares? So that's, in my opinion, just distraction. It's a deliberate way to distract from the actual experiment. So that's a lie, in my opinion, that kind of deception. Clearly, the experiment is what goes in and what the fuck comes out. That's all. That's what the experiment is. Okay, we have a box. We're throwing things. It's a magic box, right? We're throwing something into the magic box and seeing, does the box do magic? Or does the box just return what you put in and maybe it changes the direction? At a small price, 10%. Okay, so the results completely were consistent with my prediction, my model, completely inconsistent with his. So the first experiment done, the one I suggested to be the first experiment done, demonstrates theoretically, okay, the viability of what I'm arguing, because clearly I was 100% right. And it's pretty much 100%. I mean, I predicted 90%. And he was 100% wrong in the sense that his predictions of 50-50 were silly, nowhere close. And certainly his claim, okay, that 200% of the momentum went that way in the fulcrum, the earth moved, well, that's pretty unverified, isn't it? All right, now that's the 5-minute video done again. All right, so that's what I want you to argue, that here we have the theoretical premise. It's working. My model is working. And now all we have to do is put the half mass out here, or the 1/3 mass out there, or the 1/4 mass out there, and then show that it breaks down somehow. Now, I showed it on my porch oscillating. So there's some indication that, yeah, this consistently does work. And so now we have to just explain why when physicist Michael did it, all of a sudden it didn't work. It failed completely. And part of the reason why I'm going to say it failed completely is because the positions weren't quite right. And the springs aren't going to work as soon as you make the mass too heavy or too light. And I have explained all that too. So I'll explain it again in this video if I have to. But I'll wait till I have to. So that's the first big lie, is that he didn't even account for the fact that his model predicted completely wrong. That this direction crap, look, right now, you're going to do the experiment, come out with completely this result. 90% transfer of direction. How do you explain it? You've completely changed the direction of the momentum, meaning you've destroyed it. It's canceling. This amount cancels this amount, and all you have left are the 10%. And so you're saying that you destroyed all the momentum except for the momentum of the lever itself? I mean, what exactly is going to be your argument? Please, provide it. Because it fails your directional importance idea. The idea that direction matters, that you can subtract this direction from this direction, is annihilated by the experimental results. The experimental results are saying, no, that is the momentum. All you did was change its direction. It's the same momentum, you just changed its direction. No big deal. Changing direction isn't a big deal. I mean, clearly that's what the experiment's showing.
And your accusations of cheating?
My accusations of cheating doesn't involve the spring. We knew he was doing the spring. I was not enthusiastic. I basically said in the live video, I don't have any interest in springs. So if you want to waste time doing springs, that's your business. I just want to see the hard elastic collision. And you have to concede, right? I mean, I think you've done enough spring experiments to know that springs are really good at creating reflections. And that clearly, from my perspective, why would I want to introduce the possibility of a reflection? Reflections aren't of any interest to me. I'm trying to bang hard things into hard things. I'm trying to take the energy from this and put it into this. And there would be nothing intuitive about saying, let's put a spring between them because somehow that'll help. It can only get in the way.
Which I believe wholly incorrect and false. It's a good little...
So again, it's not false. Now let's just understand, he did the experiment with springs, came out with his result, and then he said he did do it with a hard bolt, and the results came out the same. Now, I guess maybe you haven't watched enough of Professor Lewin in these videos, but frankly, the formula they're using is for elastic. It's not super elastic or special elastic. Any elastic experiment, that is, any experiment where you can have the expectation that you haven't permanently deformed something, should produce the results. So it came out exactly as he predicted with a hard elastic collision, and yet he didn't show it. He didn't think it was significant. So even though it came out exactly, by his claim, the way he would have predicted it to come out, his science predicts the elastic should be elastic. Whether the spring's there or not, it should be the same result. That's their theory. It's sort of my theory too, I'm saying, but yes, it has to be, you have to get everything just right. You get something a little bit off, the spring is going to show its capacity to cause reflection. So that's the true lie, is this lie that he did it with the hard elastic. It came out exactly as his science predicts, and yet he didn't film it. That is so disingenuous, it's beyond believable as a story.
Oh, leave here. I can't whiz it around because I've got the weights strung up on it. But it was a bit of, I don't know what it is, aluminium, and it's got the it's thin wall, but it's got this pattern which gives it rigidity. Not bad for these kind of
yes, again, even the yardstick, horizontal, probably doesn't bend much.
experiments. I'm just going to pause you, hang on.
So the good news is it does appear to have very heavy weights by comparison to the weight of the lever, and that's what you want. You want like a 1 to 10 ratio if you can get it, that kind of thing. The higher the difference, the less the lever can steal from the experiment. The lower the percentage, which is the ideal.
Equal masses, equal radius.
Now the problem is here too, he does have them a little bit off their center. They want to move a little bit further, so both of them are pushing against each other at the beginning of the experiment, which is okay, because basically they will balance that pressure. So it's not verboten, but it just needs to be understood that he is suspending them a little higher than they would be. So they're a little higher on the circle. So one of them will push a little further because it's not at its 0 point. So you have to be aware that you're adding a little extra energy.
I wanted to see what sort of return on the input we
right.
get.
So the point is, some of the experiments look 85, 80. Some look 90, 95. So some are pretty, So it's not a perfect hitting surface. Apparently, it doesn't give you perfect results each time. Not consistent ones anyway, let's say. But clearly, he's showing that, again, physicist Michael is wrong. Clearly, not half the energy comes back as a reflection. So the elastic formula, that states that I have to cancel both of these because twice the energy went into the earth, isn't working. So that's the clear point here. It's obvious. So again, just concede that, well, unfortunately, your model has failed, right? It's the model you're defending, so can I call it your model? I mean, your model is failing this simple test.
To the inelastic collision.
I don't know what the inelastic collision would have anything to do with anything. Again, what would inelastic be demonstrating? So why would you even use the word inelastic in this circumstance? It can't possibly mean something.
And one with a spring interposed.
So that's not really the point. The point is it's elastic, and you can have two kinds of elastic experiment. You can have elastic with a spring, super elastic, or you can have hard elastic like the Newton's cradle. Newton's cradles don't have springs, but they're clearly very elastic. I mean, completely elastic, like really mega elastic. But obviously, if we put springs on the Newton's cradle, do you think it'll work as well? Now, the truth is, I guess if you use heavy enough objects, it probably will. The springs won't get in the way. But if you use light objects, you could imagine the springs are going to make a mess.
I don't think it's going to show a great improvement, but I was expecting there to be an improvement with a spring.
So I don't know why that expectation exists. That's the part I don't understand. Because can't you like just intuitively realize that what the spring is going to do is make it reflect, if anything at all? It's going to take some of the energy, push it in, and now it's going to take time, because the spring's slower. It's, you'd have to concede the spring is slower in transferring the energy, right, than the thing just hitting the other object. That's got to be much faster. So it's slowing down the interaction and giving you time for there to be, well, you already did everything going that way, and now the spring's just going to push some energy back the way it came. So the spring is just going to cause some reflection. I don't know exactly why you think reflection means you got the energy into the object. Reflections to me, for my entire life, have meant the energy didn't go where you threw it. Anytime something reflects, it just says to me, hey, it didn't take my energy.
As Michael used. For good reason, often these non-elastic collisions, you lose a lot of energy.
So they're non-elastic. No, these are elastic. So these aren't non-elastic. So without the spring is still elastic. So you're just getting that wrong. Without the spring is elastic. Hard object against hard object is elastic. It is not inelastic. Springs are called super elastic because it's another version of elastic.
You would expect to, with shock and the impact, vibration, one thing and another.
Yeah, well, all that one thing or another happens inside of a Newton's cradle. So I'm just saying that, yes, we know that these transfers can be very quick or very slow. But the point is that I would argue that they have to be conversion. There has to be a capacity to make the conversion. I once had it told, I remember seeing, I don't know, this is decades ago, that, cow catchers on trains were shaped because the cows don't bounce off the train. They have to be slid off the train, okay, because they're not hard elastic. Okay, but you think they're hard enough. I mean, they're a big bag of stuff. You think they're going to bounce to some extent, but they really don't. They just kind of smush off the side. So, but I haven't seen that video. So, what exactly can you hit with a train and make it bounce off the train with much more velocity than the train itself has? So the whole idea that you use a heavy thing to hit a light thing and you make the light thing go much faster than the train was going, that's the question. And the point is that no, that really doesn't happen. That you can't give it extra velocity. You can only give it the velocity that the object had. And if the object's very, very dense, very massive, then the amount of energy it's giving away is so small that it doesn't slow down. So this doesn't go any faster. If this is a smaller mass, say 2 to 1, well then this has to lose a lot of its velocity to give the velocity to the lighter thing. So the lighter thing will look like it's going faster away because this had to slow down for this to go the speed it started with. So that's where it gets kind of complicated. We don't have good experiments.
Actually, it's better than I thought.
Well, yeah, it's exactly as I predicted. So yes, so I don't know why that's better than you thought, but okay, you thought it was going to be even closer to my prediction. You know. Now, part of this other subjects here are where you hit the lever. Now that might have something to do with this whole thing. So both of you have chosen to test it at the end of the lever. Now when I did the test, I didn't have 2 equal masses. So I didn't at the time have an opportunity to do that test. But it would be interesting to see what would happen if you move them half the distance in and see if something screws it up. See if it's less efficient. See, and then part of me is a little suspicious of this nail, okay? These look like very heavy weights. This nail doesn't look like it's not going to move at all. So that might get you into trouble too. I mean, the fulcrum really has to be solid.
I'm only judging it very roughly by the distance of swing in each. This is perpendicular to this.
Yes, the velocities look very similar.
Parallel to this, sorry. So it ain't bad. So I don't know if...
So and ain't bad at decisively proving physicist Michael's prediction absolutely wrong, and in turn proving his model failed. True or not true? I mean, it's a simple enough thing. You're talking about this honesty thing. Will you be honest to say this is evidence of his model failing? This experiment shows a failure of his model. Failure, failure, failure. Right? You're all obsessed with finding one little failure in a model. Well, isn't this one little failure in the model? Your model fails entirely. I mean, it's a complete 100% failure, correct? Will you be honest and announce, yes, our model completely fails this rudimentary simple test. There is no evidence that twice the energy went into the Earth and that half the energy came back as reflections. That didn't happen.
I'm going to be able to show that. But
I mean, obviously no reflection that time at all. I mean, bang, this one just kept on going. Not even any sign of a reflection. Nothing even indicating a stopping. It didn't even stop. It just kept going. So, I mean, right there, that's probably when I should have, I probably should download this. But just watch the energy going in this case.
that.
There's the sound, but it hasn't hit yet. Funny. Alright, keeps going, keeps going. It's still struggling, but it's keeping going. It's going in the forward direction. So obviously it can't go past 0 and then reflect. That would be ridiculous. So it's clearly not reflected at all. And obviously look at the other side. It is very close to making it to the piece of wood. So, decisive evidence against your model. Well, let's just call it an interesting piece of evidence indicating your model may be flawed. Okay, can we say at least that is a minimum? I mean, of course, you'll exaggerate and say exactly the opposite when it's your turn, right? When you have evidence against my theory, it's decisive and complete. Yet this isn't really, this isn't the complete evidence. It's only partial evidence. It's only a little bit of evidence.
But
even though a failure was decisive, the failure was unmissable. It is completely not as physicist Michael predicted. Right? Now, if you can't concede that, we won't talk anymore. There was no point. Because his prediction was half
It shouldn't be any worse. I'm going to try and glue it onto one of these in a minute. That might be awkward, but the main point of this video really
It is to just waste everybody's time, apparently. Look, you have the experiment. You have a device that, I would make it a little better if you could. But why don't you do the rest of the experiments? I don't understand. This video is very disappointing because he's really not going to do anything else with this lever. So this is where it's going to end. He's not going to move them in a little bit, adjust them place and see if they get more bang for the buck. We'll see if he can optimize the positions. He's not going to do anything.
Was that when physicist Michael got the 90% transfer of energy at the first test using a spring?
Right, which in my opinion just gets in the way, but in that case it didn't, because I would argue that because the distances just happen to be more just right. So again, I don't want to confuse you, okay? But the truth is the distances do have to be just right. And if I put this one object out further, you can understand it gets heavier, which means you're now hitting a light thing into a heavy thing. And clearly it's really hard to get all the energy in. You're going to get a bounce on this side. And if I put it the other way, that is, now it's a thing with the big momentum hitting the light thing, like the train hitting the cow, the same problem is going to exist. I'm going to get a bounce because I really can't get the energy into this. It's too light. I can't get it going fast enough. My deceleration won't match its acceleration, and I won't be able to give it the velocity. So I'll have to bounce again, or I'd have to plow right through. So the distances really do matter. Incredibly important. And in the case where you're losing 10% to the lever, you have to understand that the distances probably have to be adjusted for that 10% you're losing.
You were gushing about that he was wrong there because he was predicting a loss of energy.
So that's not what I said. But obviously what he was predicting isn't the outcome. And isn't that sort of important here? That one of his predictions was decidedly wrong. That's an indication that the model is incorrect. You won't concede that?
Which you would, being a non-elastic collision. You would think so.
It's not non-elastic. So again, he didn't do any non-elastic except for the clay experiments, which obviously were garbage because more than half the energy was absorbed by the clay.
But he was using the spring and it transferred the energy quite well, 90%. And then...
Right, proving my model accurate.
When he did the half mass at twice radius, and that didn't match your prediction, then suddenly the spring was at fault.
Well, I'm saying that the spring allows for the reflection, so I'm just saying that it makes it more sensitive. So you've added another variable to get in the way. That's what I argued. Okay, I didn't argue anything other than that the spring's not going to help. And the fact is, we didn't see the experiment I described, and I think everybody, if they had to take a lie detector test, were saying they wanted to see, was just bang the object into the lever and see what happens on the other side. Don't put anything in the way.
When there was no problem with the spring in the first test, when he did transfer the energy, equal radius, and then when he did the half mass, 2 radius, and
I would argue that it didn't help. That's my whole argument. Okay, so it didn't help, and it obviously didn't hurt enough to fuck up the experiment. Now maybe the lever only absorbs 5% of the energy, and it absorbed 10 because of the spring. We don't know.
I don't know if somebody could let me know. Did you get a roughly 1.4 as we would expect?
Well, you didn't pay any attention. He kept talking about angular momentum. He didn't give us those numbers. He didn't emphasize. He just says it's somewhere in the range of elastic and inelastic, which is somewhere in the range between 100 and 0. So it was very unhelpful, his numbers. He didn't show momentum in, kinetic energy in, momentum out, kinetic energy out. He didn't do that simple thing.
It didn't go twice the velocity as the input. We'd expect it to go about 1.4 as fast. I don't know. Somebody leaving.
Obviously, in the case of 1 to 3, which I think he did do, it's not going to be 1.4. It's going to be some other number, 2.2 or something.
Comment if that was the case. When that happened, Gary then suddenly blamed the spring.
So that didn't happen. So this, your video is a little bit, full of lies again and misparaphrases. You could quote me where when that didn't happen, blah 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 blah. Okay, because again, there's lots of reasons to be wondering about the experiment. Clearly, the one object was always on the end of the lever, right? So you can see that, right? The leaving object was always at the end of the lever. And then you banged at the end of the lever or you banged in the middle, and you have to concede that those are different things. Now yours are inside the end, so obviously it's almost like the same. You're not going to mean anything, but he did have it the very end of the lever in the middle of the object, which means that even when it swings, it might slide right off the end of the lever. So it wasn't exactly perfect for lots of reasons.
That was a terrible idea to use a spring, blah, 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 blah.
I said that right from the very beginning, and I don't know how you can't understand how the spring just gets in the way. Its only use is to create reflections. It really can't do anything else useful except make reflections. Clearly, I'm not interested in reflecting the object, so why the hell would I want a spring in there? So if you can't get that by now, I guess you'll never get it. Why would springs be of interest to me?
But you didn't complain about it in the first test when we...
Yeah, I did. Okay, but the point was I said even with the spring, he got 90%. So even with a spring that's going to induce reflections, even with it, it still worked pretty well. That's what I said. Amazing.
When he got 90% of the energy through. You can't have it both ways.
I didn't have it both ways. I'm just accounting for, look, clearly he failed the first test. His model succeeded in subsequent tests. My model succeeded in the first test and fails in the subsequent test. Now, you can probably figure out that there's probably something wrong there. For both sides. You have to explain why it's failing here. I have to explain why it's failing there. Now, you chose not to even acknowledge the failure here. You're not even acknowledging your model is failing. The math is failing. The whole theory is failing. You're not even acknowledging it, let alone explaining it. I'm saying I never suggested springs, so I'm saying there's a variable you put into the experiment I have no interest in. I don't want to see springs in the fucking experiment. I said it right from the beginning. It's of no value to producing what I want, which is a clean transfer of the energy between the two objects. I don't want anything interfering with the transfer. I mean, I made all of that clear in drawing after drawing after drawing after drawing. So to sit there and pretend that, of course, I'm going to say, well, if I have to find something that's wrong right from the beginning, I'm going to say, yeah, that fucking spring shouldn't have been there. Or you should have done the experiment without it. And he claims he did do it without it and got the same results. The results that confirm his theory, and yet he didn't video it? Again, you think that's a genuine story. He got exactly the result he was looking for and didn't video it.
That's dishonest, isn't it?
That's dishonest, isn't it?
That's just not good, fair.
I don't see where it's unfair. I objected from the very beginning, and I'm saying, yes, the fact is this isn't going to be consistent when you put the mass twice the distance out there. All of a sudden, a completely different outcome is going to take place. And I'm saying the only thing that can explain that is that the distances have to be wrong, and the spring is making that obvious. Because now it either weighs too much or it weighs too little, and the spring is creating the opportunity for a reflection.
Argument. So, come on. Right, let's glue a spring on and see if it makes any difference. Well, after having thoroughly stuck my fingers together with super glue.
So this is not a good idea, okay? Because now he has the objects further from the lever, and he's using a really hard spring. So this spring is really stiff. This is, you know, Steve's springs were really flexible, so very different in a way. And obviously, so this distance is going to be always there. So just recognize it's starting from an inch further out. So obviously, this is going to push all the way through. This is going to only travel part of the arc. It's not going to be in the gravity as long. It's not going to be fighting gravity as long because it's going to travel. The distance, the total distance it has to travel is less by this inch plus, where this is not going to change. This is still going to go all the way to its 0 point. So it's going to plow right through that, and this is, you know, its real 0 point is somewhere over here. That's where that's its velocity. So this is a little deceptive.
We've got a spring on each mass now. It's liable to...
Right, so there weren't springs on each mass in Steven's video, so you probably don't need 2 springs. There wasn't 2 springs in his video. So if you want to analogize, you probably should do it more directly and just duplicate the experiment as he did it, not as he didn't do it.
It'll fall off at any minute.
So this went all the way back to the board, but it did so again because this center of mass is here. The center, the place it wants to go is here off the edge of the table. It still went there. The other object started an inch forward. And so it, okay, you have to start counting its movement from that point to that point. So the distance has been adjusted forward. So of course it went further, but it didn't really go further. Okay, the total distance it traveled isn't the same as this object. This one traveled more total distance. I mean, all of this, again, the argument is all this has to be done a little bit carefully. These are important variables, and he's just pretending that we don't have to pay any attention to all these little variables. When, yeah, you do, unfortunately. It all matters.
It's very subtle, but it's certainly no worse.
All right, so this one's center of gravity is now here because it's not putting any pressure. You can see it wobbling there. So its center of mass is here. I don't know where this one's center of mass is. It definitely seems like this one was pushing more against it, but can't say for sure. So maybe he's moved the whole... Well, he can't have moved anything. Yeah, I don't know. Yeah, so maybe he's moved the whole experiment. So he moved it forward. Moved the board and the lever thing forward a little bit. So the springs were barely touching. So that's about the same. The other one did seem like it got even further, but it did seem like they were both against the lever in the other one. I don't know if we could look at the 2 experiments and see if we can see any change. So this note paper is about that far. Let's see if it's the same distance in this one. No. So he did move it between the 2 experiments. See this little piece of notebook paper? It's changed position. So there. Let's see if we can go back. So that's no spring. All right. So we have to go to the first one with the spring, which is this one. All right, so that's the first one with the spring. Let's just see if the second. Okay, all the spring ones looks like it stays the same. Okay. So he did move it between the spring experiment and the non-spring. He did move the board. Okay. So now they're just resting against here. They're not really pushing into it as I thought they were.
We've got a spring on each mass now.
All right, so you can see that one wobbled a little bit when he touched here, so he barely touched it. So they're barely touching the aluminum. Okay, so it is a fair test.
Now it's liable to fall off at any minute.
So, but again, there was no spring on the second object in Stephen's experiment. No, Michael, sorry. Why am I calling him Stephen? That's so funny. Anyway, physicist Michael. Sorry. See, that's really close. I mean, damn. I mean, that's really close. So you know that the potential goes up a little higher. You get this, potential to move this lever with even less losses. But it's hard to imagine that it's zero. But anyway. And you have a little tiny reflection here, maybe? Yeah, you do. A little bit, maybe. Well, that's just maybe the oscillation of the pendulum. So, I guess
it's very subtle.
Yes, it's very subtle. And the point would be is, maybe if you're filming enough times, you'll get enough numbers to, say, okay, what's an average? But clearly, getting the one to almost hit the board was really quite good. I mean, it's better than 90%.
But it's certainly no worse.
So this one isn't touching at the moment, so maybe that's the catch. This one is a little bit further back than the other one was. So it does have a slight advantage. It's going to travel less distance. That's why it looks like it traveled further. Alright, so not quite as good as that first one.
Yeah, it's certainly no worse.
So we can see this one's really not touching it because it is wobbling still. So it's a little bit further back. You can see it's not touching, it's still wobbling.
Yeah. I think it's slightly better than just the completely...
Well, I don't know, slightly. It's pretty good. I mean, it's like you went from 90 to 95%. But again, that is probably because you did move the board. So you've changed the experiment a bit.
Non-elastic collision.
So again, every one of these experiments prove my model right and physicist Michael's predictions wrong. And instead of acknowledging that in this video and pointing out how, well, physicist Michael sure was kind of dishonest not to point out how his model failed the first test, decisively failed it. Doesn't make any sense. Didn't provide any explanation for the failure. He didn't explain why his model completely fails, where he destroyed all the momentum essentially, because he ended up making it go in two different directions, which means it all canceled and it's zero. So he put 100 momentums in and he got 0 momentum out. That's physicist Michael's statement, pretty much. His complete failure.
But anyway.
I mean, there's nothing to go into the fulcrum. He used it all up going, with the energy going back this way. The complete 100 was canceled. You can't make it go somewhere else too.
I mainly wanted to defend physicist Michael about the outrageous accusations of cheating.
Okay, so anyway, they're not outrageous in the sense that he still has the 6 experiments, or whatever you want to say, the 2 groups of experiments where he got free momentum out of the experiment. And again, there has to be some accounting for that. If you're going to make free momentum, it just can't be thought of as being trivial.
Anyway. See you in the next one.
Okay, well, let's see if we continue to do the experiment. Then I won't have to, thank you. But we'll see. I doubt that I won't have to, because I doubt that you'll clean it up make it as good as you can. But we'll see. But yes, I mean, obviously, kind of, we want to get to the changing in the masses. And ideally, the experiment should be done from, incremental. Take the two at the same distance and then just start moving and changing the mass. Change the mass and then try it over a various number of locations and see how it changes in terms of how much is converted and how much is reflected. Because there is some point where you're going to get a peak conversion. And the point is if at the peak conversion you have zero reflection, then you have, in my opinion, proven the experiment. And it's going to be proven my way. But okay, we'll wait and see. Alright, take a pause here. I don't know if we need to read any comments, but we'll see if there's anything civil or rational. Alright, since I'm here, I might as well do the comments. So the John Sean Walker guy, little Johnny Walker, says mass number 2 is supposed to receive the same amount of velocity, energy, and momentum as mass 1 had minus losses. So again, he's talking about the magnitude, but the direction is completely wrong. Okay, so again, what's the point? So this idiot is arguing his own physics in the middle of this argument between the conventional physics and my model. So this isn't what Professor Lewin says has to happen. Okay, so it's just wrong. It's not the prediction. Their prediction is physicist Michael's prediction. So not this prediction. Okay, where he's saying only 100% of the momentum goes into the object. Lewin clearly states it's twice the momentum that goes into the non-moving object, the fulcrum, in this case. Alright, can't yet get exact because I'm using tablet. Okay, so he's attempting to do whatever. He's processing the video, which doesn't seem to make much sense. I mean, it obviously doesn't seem like you're going to get very good frame rate numbers. Let's see if there was a reply like this. Oh, so let's go look at what he's put out here. He does he spends all this time. He can't make a video, can't do any of this stuff. He's doing this. So yeah, this is obviously tilted, so that's not very good. Doesn't mean much, okay? Because you have to, So load sound, I don't know what that means exactly. But anyway. It's amazing how the camera angle changed so dramatically too. So you can see where the card over here, you can see that these experiments, you can see that the board itself was moved for the two experiments. So the objects were further away from the lever to account for the spring. Okay. So we really don't need any more of that, whatever the hell that was for. There's going to be a solar eclipse. Well, that's really silly. They had a perfect one, okay. On the 98th anniversary, or the 102nd anniversary, on the 98th anniversary of the Eddington experiment, they had a perfect eclipse and didn't take any advantage of it. A perfect eclipse. 12 noon. Alright, complete. 99% eclipse at 12 noon. I mean, couldn't get better. Over North America. Alright, so this is just nothing. So we have no comments of any use. So nobody acknowledging, boy, doesn't this prove physicist Michael prediction wrong? I mean, yeah, it does. Yeah. Yeah. But let's not account for that. Let's not explain why it's wrong. So why he got the wrong prediction, why he made the wrong prediction. Maybe you could even say that. Why did he make the wrong prediction? Alright, anyway. So, he has a new video up for this, Michael. Buoyancy and Newton's third law. So, I would argue that Newton's third law is kind of just crap in the sense that it's really not about an equal and opposite reaction. It's about every explosion explodes in both directions, so that's a giveaway right there. And sort of more importantly, okay, when you bang into something, to give it momentum, you have to give it your momentum. So something has to be given momentum. And when you give something momentum, there's no opposite reaction. When you give away $10, there's no opposite reaction that makes you $10 poorer. You're $10 poorer automatically. So it's really not perfectly worded. So maybe we will be responding to that video. I don't know. It seems like a pretty radical change in subject. So maybe it's, it's better than him talking about galaxies, the birth of galaxies, or some other kind of crap. So anyway, we'll see, and such and so forth and whatnot. So that's enough of a video on this, I guess. So yeah, I don't know when I'm got a bunch of projects. Can't really do them if I'm making space for the experiment. So I'm gonna have to figure out how to make space and continue doing what I have to get done. But we'll see. Till the next time and such.